It just gives you random jokes.
Oh yeah, that's old school.
And Cowsay, which
I'm not familiar with that one.
oh no.
You have to pipe it.
So yeah, you do. So we can pipe fortune into Cowsay. And the cow tells us the quote. So if you're ever feeling down, I really install, and your cow can tell you stuff. Okay.
That's awesome.
That is awesome.
That's the kind of thing I came here to see.
Yes. That's probably going to be the highlight of this whole hour.
Okay. So let's get into edit distances. So what is an edit distance? This is my Google search earlier. It's like, how does Google know what we mean, even though we half the time don't know spelling? So this is a common problem in the field of information retrieval, where you're trying to retrieve specific information from a database, but there's either the information in the database is spelled incorrectly for text, or maybe the information you're using to search is spelled incorrectly or mistyped or misentered or whatever it may be. A lot of the edit distance algorithms, not the ones I'm going to go over in detail, but a lot of other ones are actually just similarity algorithms or similarity measures, which can be used to compare different things. Like dynamic time warping can be used to compare two audio signals to see if two songs are the same song. But yeah, so an edit distance is specifically for text or strings usually, and it can also be used for things that can be represented that way, like DNA sequences. But what you're trying to say is you're creating a metric to distinguish between two different strings. How different are they? How dissimilar are they? And so let's see. So like at the bottom here, I've got some examples. Really, it's based off how many operations would it take for you to get one of them, one string to look like the other. So cat, if you just add an R, you get cart. So they're pretty similar. They're one edit operation apart. Form and from, which I do all the time, that's just a transposition of switching two adjacent letters around. And neighbor and neighbor, you have to remove two letters and add one. And so that's a little far off. So that might be confusing for people. So I'd recommend naming your company Neighbor spelled the normal way. So operations, some examples of operations is an insertion, a deletion, or a substitution. They're pretty self-explanatory by their name, but the idea is you add a character, you removed a character, or you changed a character. So actually, if we go back, neighbor and neighbor can be done by removing one letter and making one substitution. So there's more than one way to get there. So that's part of the trick when you're actually implementing these things, is determining what edit operations you're going to use, because some of them will introduce more complexity than others. Some additional operations, transposition, where you just alternate two adjacent symbols, their position. That's a very common one that's used by many edit distances. Less common, but used a lot in OCR, optimal character recognition, is merging and splitting. Merging two identical symbols into just one copy of them, and split is the reverse. So
those are kind of, is it fair to say those are special cases of delete and insert?
Yeah, you could say they're special cases. And so what's cool about this is you can see all of these are useful, especially for names, which is actually where I first got introduced to edit distance, is doing research with a professor of economics at BYU that uses genealogical records to do economics research. And so one of the big things he's working on in combination with family search, actually, is to be able to figure out how similar two names are to each other, to say, is this the same person and their name was just misspelled, which happens a lot. So you can think of merging and splitting being very useful as far as like two L's versus one L or different things like that, or a transposition, an EI and an IE. Alec might run into that. So those are some additional operations. So going into some of the distances, there's the Levenstein distance, which was first thought about in the 60s, Vladimir Levenstein, and it uses insertion, deletion, and substitution. Those are the three that it uses. So I didn't want to write this all out, so I took a screenshot on Wikipedia. You can see my beautiful source there. But if you have studied mathematics recently, this notation looks really familiar and comfortable, and if you haven't, it might look really weird. So basically, Lev subscript AB is a function, and what it's going to return is the distance between two strings, and the parameters it takes are the length of the two strings, and the two strings themselves are those subscripts. So it takes 4 parameters, but we're really going to care about 2 because this actually recurses on itself for the same 2 strings. And so I and j are basically the index that you start at. So how many of the characters in the word are you actually looking at? And so you start with the full distance, which is what that absolute value or those 2 pipes on the side of A and B is the length. So the length of the strings. And so there are 2 different cases, really 4, but is the minimum of the 2 lengths 0? So is one of the words the empty string, meaning it isn't a string? Then if so, the maximum of the 2, the length of the other, is the difference. So if they're both the empty string, then there's no difference between them, right? You get 0 difference. But if one is the empty string and one is supercalifragilistic, however you say it, then it would be the length of that word, right? So like cat and the empty string the difference would be 3 in this case. So that's kind of a really obscure case, but they take care of it because edge cases have to be accounted for. And then otherwise, it's the minimum of one of these 3, which are actually in order from top to bottom, I believe, yeah. Insertion, deletion, and substitution. Because what you're doing is you're adjusting the index you're starting on and then adding an edit operation. So you're gonna say, oh, if we just look at 1 fewer characters, then we can say that's an edit operation. And it gets a little convoluted, and if you're not following exactly, that's totally fine. But you can see it recurses on itself, and it says, so if we're comparing cat and dog, then it would be, we would recurse into comparing like dog and hat, and we would compare caw and dog, and we can compare doe and cat and og and cat. And you can see it gets complicated, right? That's not gonna be super efficient. And the naive way of implementing it is very high complexity because you're comparing all the substrings against each other. You can ignore the indicator function stuff if you want, or you can read it and enjoy it like I do. But just saying, like, if the characters we're comparing are the same versus if they're not, we will assign an extra value. That's just so that you don't consider like an LL a transposition of LL, so that you wouldn't account for that. So that's Levenstein distance, and so it's a fun one if you want to learn how to do recursive programming. But it's a lot cooler if you want to learn dynamic programming. So that's the algorithm I'll pull up. This is just pseudocode from, again, Wikipedia, but it's pretty good for implementing Levenstein distance using dynamic programming. And it uses a bottom-up approach. If anyone's ever had to do a knapsack problem or something like that, it's similar, where you start with basically all the comparisons to like the empty string. So we know eventually in our recursive algorithm, we get to the point where we're comparing like a single letter against an empty string. And so know those are all 1. And basically you can build out a matrix. This is a topic for another time, dynamic programming approaches. But you can build out a matrix and just calculate the values for each part of the matrix that lines up telling you between the one letter of one word, like the second letter, and the second letter on the other word, then you would go to the 2 spot in your matrix, and you would see the value of what kind of edit operation you had to do to alter from one to the other, if any. Maybe they're the same word, and so every character is the same. But the way that works out is you add, you're building on itself, and so the last value of your matrix will actually be your Levenstein distance, and it builds on calculating every intermediate value, but doesn't require you to compare every substring against every other substring. So it's actually really cool. So it's using the Wagner-Fisher algorithm, which is order NM, where NM are the lengths of the strings, which is going to be a lot more efficient than your recursive approach, unless one of them is the empty string or something like that. Those edge cases can be faster with the naive approach. And you'll see down in the bottom, it's still doing those edit operations, deletion, insertion, substitution, the way they were defined previously. So it's pretty cool. And then there's the Amaro-Levenstein distance. And so Frederick Amaro is one of the fathers of natural language processing. He wrote the first patented algorithm for IBM that inserts hyphens into words intelligently. I didn't know you had to figure out how to do that, but I guess you do. So that's pretty cool. And he had some other approaches. So he didn't actually build on Levenstein's model, but Levenstein and Damaro's kind of thoughts got merged by other, mostly linguists, to come up with this model, which looks different because they're using slightly different notation, but really it's pretty much the same, except it includes transposition, whereas Levenstein didn't include transposition. So it couldn't account for M and N being switched as one edit operation. It would have to be either some deletions and additions, or substituting one and substituting the other. So transposition means that if two letters are switched using Amaro-Levenstein distance, you're actually going to get a smaller edit distance than Levenstein distance. So you would consider words with a transposition, which happens a lot when you type, to be more similar than Levenstein distance would. So Amaro-Levenstein is going to be a lot better when you're just trying to account for user input being a mistake when they're typing and getting the order wrong.
So am I right in reading the formula, it does take into account transposition, but it doesn't define it as strictly neighboring characters? They could be. It does.
That's, if you see the very bottom one where it's saying -2 and -2. It actually is accounting for it. They have to really? They have to be adjacent, and that condition on the side, and a sub I equals b sub j minus 1.
Oh, I didn't look at that carefully enough. Okay, I see that.
B at j.
Okay, okay.
So that's where it's looking at two different characters, and they're in one at index 4, and the other one at index 5, and the other one at index 4, and the other one at index 5. They're just
gotcha.
So
okay, cool.
This is the beauty of abstraction right here. That's why I love math, because you can take a problem like how different are two words, and you can turn it into this. So again, you can use basically the same approach, just adding that transposition in on the bottom. This is slightly different, but the algorithm is the same. And it uses, again, Wagner-Fisher algorithm to do this dynamic programming trick so that this is basically order n times m again, but not quite. It's a little more complex, just because you're making an additional one. So actually, no, it's still order n times m. The leading behavior is slightly different. So, but we don't often care about that. So that's Amaro-Levenstein distance. Then one that's pretty different, I'll start into by talking about Gero similarity. Gero Winkler is going to be the one that we're actually talking about. You have to start off with a discussion about similarity though. So it compares two strings to see how similar they are, whereas what we've been talking about up until now is how dissimilar are two strings, how different are they? So just looking at it from a different side. The similarity pretty much just uses transposition. Again, you can kind of consider some of the operations to be combinations of other operations, so it's not exclusive, but it's considering transposition, and it's a little more complicated to wrap your head around, but the general idea is you're gonna say, how many characters do the words have in common? How long are the words, and how many transpositions does it require to get from one word to another? Like how many transpositions are there, just looking at them as permutations of the other? So I guess what I just said was incorrect. Not how many does it take to get from one to the other, but just how many transpositions exist. Like you have a CK in one and you have a KC in the other, even if they're in different sides of the word. And then it is essentially weighting the matching characters according to the lengths of the strings and averaging them to get a similarity measure. One caveat with that is that characters can only be considered matching if, one, they're the same character, but two, they can't be too far apart from each other. So you take the maximum of the two lengths of the words, so whichever one's longest, divide it by 2, and that notation is floor. You can see the bracket only goes on the bottom. So floor it, and then subtract 1. So it's basically, they can't be on complete opposite sides of the word to be considered matching. So that's just another caveat. Then, so you can calculate that similarity out, and using that similarity, which is gonna be sim j, the little subscript j, you can calculate the Jarrow-Winkler distance, which is going to be 1 minus the Jarrow-Winkler similarity. So it's just these people, their approach was similarity, not difference. So if you look at it, the cool thing that it does is it's gonna weight according to the prefix. So if two strings have more at the beginning of the words that are in common, like regenerate and revive both have RE in the front, that's going to be weighted into the similarity, and they're being considered more similar for that. And so you can see exactly how that works, but that's the general idea, is it's going to weight towards the front of the word, and you can kind of tune it. It's not a fixed thing. There are some usual values. As you can see, Winkler used 0.1 for the value of P, for instance.
And is this, I think at one point I heard you say this was useful for name similarities?
Yeah, so in the research that I was doing, we weren't researching different methods, different edit distances. We were just trying to figure out how to effectively calculate the distance between names as part of calculating the distance between two genealogical records. But we did find that Jarrow-Winkler was a lot more accurate for what we were doing when we were considering names, and we figured that was because the front ends of names tend to get used, like even if you have a nickname, but we didn't ever like confirm that.
Matt and Matthew.
Yeah. So there are other nicknames obviously that don't come from the first of the name, and often the first can be misspelled. But that was something interesting we found. However, it was more computationally heavy, more computationally complex, and so it took longer to do those operations. So that's Jarrow-Winkler distance. There are a few others that are worth mentioning that you might come across. Cosine similarity is a huge one. It's used a ton in machine learning and information retrieval, which often go together now, and in the study of networks. So cosine similarity is a big one. It's actually really cool. If you ever studied math and learned the law of cosines, it's just doing that. It's calculating the angle between data if you turned data into like Euclidean space in however many dimensions you need. And it's just fascinating to me.
That sounds magical.
Yeah, it is. And so that's one that you'll see a lot if you're looking at stuff about machine learning. Trigram Similarity is actually in PostgreSQL. Like you can just do it off the cuff, but it takes groups of 3 from the word and compares those against each other. Hamming distance only allows substitution, which is kind of interesting, and I don't think makes as much sense for English, but people use it. Graph edit distance treats the string as a graph or a network where the letters are connected to each other. And the edit operations are graph operations, like if you had, links in a chain is essentially what a graph is, or a network. And you were like removing one of those nodes or adding a node or removing an edge between them or adding an edge. So that's pretty cool. And then time warp edit distance and dynamic time warping just sound really cool. They do time series matching. So things that are happening in different amounts of time. Dynamic time warping gets used for beat sequences. When you're comparing musical data, I did a whole research project on cover song recognition. So like if you're listening to Guns N' Roses Knocking on Heaven's Door and Bob Dylan Knocking on Heaven's Door, how do you tell that those are actually the same song? Because it's not the same problem as Shazam, which is basically trying to say, is the audio file I'm hearing equal to this other audio file? So you have to adjust for time. So people use dynamic time warping for that, or they use the 2-dimensional Fourier transform, which is also so cool. I'm just throwing stuff out there. If you ever want to talk about these things, happy to talk about it. So those are just some other ones you might come across.
This is the agenda for the next couple MindGardens.
Go through every distance.
Yeah, if you actually went over the algorithm that Shazam uses, that's pretty fast. They put out a couple of interesting.
Well, they use fingerprinting to make it more efficient, which is cool.
Yeah.
And then basically just in comparison, I talked a little bit about this along the way. Like obviously, if you really want to consider certain aspects of misspellings or something, you should use a distance that uses that. So if you know more about how each one's calculated, you would know which one you want to use. Basically, that's all I've got.